LASP lecture before, so about half of you. This is not your normal LASP lecture. The scientists, most of the scientists, we do have some distinguished scientists here tonight, most of them are off in a conference in San Francisco, and so that's why they asked me to talk, because the rest of those guys are not here. And so there won't be your usual spectral plots, there won't be any chemical equations, there won't even be a F equals MA equation up there. So if you're here to see good science, you're also on the road to Hong Kong. You're not in the right spot. But what I am going to talk about, as Laura said, is kind of the mission operations that we do here at LASP. And I'm going to give a little bit of background about LASP and kind of the bigger picture about what we do in the entire facility, because if you've been to lectures, you hear a lot about specific science projects, but I don't think you've ever heard of the overall what we do here. And then I'm going to focus on the mission operations and how we spacecraft and we involve our students. So, what does Star Trek, NASA, and LASP have in common? We all operate spacecraft. And why is LASP different than Star Trek or NASA? Because we have students. So this was in the daily Boulder camera a couple years ago. We get in there quite a bit when we talk about our NASA spacecraft, and we've had a few graduates from CU actually become astronauts. But this was mainly from LASP. I mean, there's NASA, there's Star Trek, and the next uniform for space professionals should be a CU-Boulder shirt because of what we're doing here. So a little bit about LASP. We're a research institute within the university. There are academic departments which are focused on astrophysical planetary science, atmosphere, ocean science, aerospace engineering. I know we've got some aerospace engineers in the audience. We also have institutes in the university that are tied to national institutes, like NIST, we have GILA, and then we have Cooperative Institute for Research in Environmental Science tied to NOAA. LASP is unique in that we're not tied to a national institute, but we do have most of our work coming from NASA. And we'll talk about the NASA programs that we're involved with. But we're pretty much a standalone institute. We draw scientists. We have faculty members from these academic departments who are also part of LASP. But we are funded mainly by competing for contracts with NASA. This is the cool thing about LASP. We do science, we do engineering, we test our equipment, we do the mission operations, we do science operations, we process that data, and it's a full closed loop within one research facility. The unique part about it is that we have students involved in all aspects of it. The students are involved in the science side, from they're going for their master's, their PhD, postdocs, and they're doing the science for their degree. On the engineering side and on the mission ops side, we employ students as part of our workforce. They actually get paid for being here. We recruit them from the university. You have to be a university employee you have to be a university student to be employed here. But we actually go out and we try to bring students in, their computer background, their mechanical engineering, aerospace engineering, and I'll talk more about our students in mission ops, but these are paid positions. So I mentioned that we're this full cycle science. It's the way I describe it is we have scientists and they come up with the problems. They kind of define the science question. They walk down the hall and they look to the engineers and say, hey, I don't understand the atmosphere around Mercury. Can you help me build a spectrograph that will help do the science to understand the atmosphere around Mercury? The scientists with the engineers go and build it. We have hardware facilities here. We have design facilities, we have a machine shop, test facilities, and it's all in the same spot. So you're working in a very small group with a lot of people. We just recently moved over to a building across the street with our scientists. So we do have to cross the street now to talk to each other, but it's not that bad. So we take these experiments, we bring them up, take them up in space, collect the data, use other resources, labs, telescope, theory, develop the understanding of the science, and then pose the next question. Again, it's that closed loop of asking the question, developing the instrument, sending it to space, collecting the science, asking the next question. One of the coolest things about here is when you have the scientist and he put up his instrument and the data comes back for the first time and they say, I didn't expect to see that. Then you know you're pushing the boundaries of science, and so it makes it a very rewarding experience here. But it's really one of the very small number of institutions that can do this full cycle science. There are other institutions, but they're either missing something, and a lot of them, very few of them actually can do the operations part of it that I'll talk about later. A little bit about the science. See, no equations, no spectrum graphs. We do solar influences, and if you were here in October, you heard Gary Rotman talk about a program, the Solar Mesosphere Explorer. I'll talk more about that a little bit. Planetary science. I'll show you some of the planetary missions, but one that we're working on right now is called MAVEN, and MAVEN is the next Mars mission to launch. A couple weeks ago, NASA launched the Mars Science Laboratory, MSL, and that's on its way to Mars. MAVEN is a program that the lead scientist is here at LASP. We're building some of the instruments here, and we're going to be operating those instruments from LASP. And that's going to be launched in 2013. Atmospheric science. This is a really cool picture of what? Noctilucent clouds, otherwise known as polar mesospheric clouds. We operate a spacecraft called Anomaly of ice in the mesosphere, and this is what these clouds, very high altitude clouds, look like from the ground, and we're imaging them from space and studying them with an instrument that we built here at LASP, and we're doing the operations for that, as well as the processing the data and sending the data out. In space physics, we do a lot of work in the space physics area, trying to understand the solar wind's interaction with our magnetic field. We have a program that we're working on called a magnetospheric multi-scale program. This is one that has 4 spacecraft flying in a very highly elliptical orbit in formation, and it's got 11, 12 instruments on board, all the same, and LASP is building several of those instruments, and we're also going to be operating the instruments from here. And NASA Goddard is operating the spacecraft. So that's the type of science that we do. Now, as far as the history, LASP has been around since 1948. We started putting experiments on the German V2 rockets that were brought over at the end of World War II. In the 60s and 70s, we started building instruments for NASA. And if you look closely, you see all the planets listed, including Pluto, which we still consider a planet. And that's because when we launched, we have an instrument on New Horizons, the student dust counter. It was still a planet, so we still count it as a planet. So LASP has sent, or on its way, an instrument to every planet in the solar system, and there is no other institution in the world besides Mother NASA that can claim that. So that's pretty impressive for being a university institute. please feel free, if you have any questions, raise your hand, or we can wait till the end. Yes?
What was the Goddard mission you were talking about?
The one with the 4 satellites, magnetospheric multiscale. And that's looking at magnetic, the interaction of solar wind with magnetic field, a physics plasma interaction called reconnection. And so they're studying that. And that's a 2013 launch also.
Is that looking at the Earth's magnetic field?
Earth's magnetic field, right, right. So now I'm talking a little bit more about the mission operations part of it. I hinted at the science that we do and the engineering, but the main talk is going to be about the mission ops part. So in our mission operations area, we have about 100 people total working in mission ops. About 50 are professionals and 50 are students. We develop and design new systems. Our latest spacecraft that we're currently operating is called Kepler. And if you were watching the news a couple days ago, actually on Monday morning, Kepler scientists announced that they actually have found an Earth-like planet going around a star very similar to our own sun. And the guys in the control room were the ones that operated that spacecraft and operate it today to enable that science to be collected. And if you heard the talk, Kepler is looking for planets going around stars that are similar to our sun, and it's looking for Earth-like planets. So it's to get an Earth-like planet in the habitable zone where water could possibly be on the planet, you need to see it 3 times. And so within the first few days, they saw this planet go in front of the star. It goes in front and transits, so there's a little dip in the intensity. And then they watched it the next year, and then last year they caught the 3rd one. And Kepler has been one of these spacecraft that isn't always well behaved. Spacecraft, we have a tendency for our spacecraft that they know we're coming up to a holiday and they have problems. And Kepler is leading the pack with Christmas. And so our folks, the last 3 years now, have worked Christmas Eve and New Year's because there's some funky thing going on with Kepler. But right after we got back from recovering the spacecraft, it had a problem. It wasn't looking at the planets. We moved it, and it caught that 3rd time for that Kepler 22b planet to be found. So pretty cool. As I mentioned, we integrate the professionals and the students in the ops and in software development, as well as the data processing. We do the data processing. We operate spacecraft and payloads. We have the operations room out here that you'll see is for Kepler. And then we have a back room where we operate 3 other spacecraft. I'll talk more about those. But again, it's one that is fully integrated with professionals and with students. So we talked about the early days of LASP, and we didn't start doing operations until this Solar Mesosphere Explorer in 1981. So if you kind of look at the history of 81, we've been operating quite a few spacecraft. A lot of those, one of them is actually the Snowy mission is one that we actually built here at LASP. So we built the spacecraft, we built the instrument, we did ops, and we did the instrument operations, the whole 9 yards. Some of these others, we just are doing mission operations. Some we're doing both mission operations and instrument operations. And not on this chart is we do quite a few instruments. We have an instrument on Cassini taking data about Saturn. We operate that instrument here. We have an instrument on the Solar Dynamics Observatory. And we don't operate the spacecraft, but we operate the instrument. So what I do is, what I talk about now is this Solar Mesosphere Explorer. This is one that really was the first time that we started doing mission operations here. This was taken out of National Geographic in 1984. Picture of professionals and students. I'm not sure who these folks were, but so this was actually a picture though from the control room that we had operating that spacecraft. It started back, there were certain things that led up to being able to do mission operations here. It wasn't just, you buy the equipment, install it, and throw the switch on. We were doing the high-speed data delivery with Mariner 9. If you ever go down to the lobby, you can see the engineering model of Mariner 9 sitting downstairs. That was the first spacecraft to ever orbit a planet, and it orbited Mars. And we had an instrument on there. And we did interactive science analysis with that. OSO 8 is a spacecraft that Ball Aerospace built, had a microprocessor on board, and we were involved in the real-time telemetry and command for that. So that was back in the 70s. We were on the cover of Aviation Week, so when we brought Solar Mesosphere Explorer, there were some real innovations that had to take place. The idea of a university, so back then everything was NASA. It was NASA operations. The 70s were the Apollo days. NASA was used to operating spacecraft from their own facilities. It's complicated, it's expensive, the satellites are very expensive, and so NASA was used to having their own professionals that are NASA employees operate it. And here comes along a university that says, hey, we can operate this thing. At that point, NASA took a huge jump to think that they would be able to turn over a expensive satellite over to a university to do operations. We had to convince them that we were able to do that. We looked at common hardware and software for test and operations, and I'll talk a little bit more about that. That was really key to a successful mission, is the same software and hardware that we used, that was going to be used to operate the spacecraft, was used in the testing of that spacecraft at Ball Aerospace. So that was one of the things that helped us be successful. And it paved the way that's a routine way that we do system testing today. And then the student involvement. Again, you can imagine NASA. They have highly paid professionals who have gone through lots of experience, and now they're going to come to a university and say, okay, university, we'll let you fly it, and you can use students. So the managers, the people that watched over this Solar Mesosphere Explorer took a real leap of faith in letting us take on that mission. When we were talking about doing this mission, we had to get ready for it. There was a warehouse on 55th Street in Boulder, and that's where we were located next to our engineering facility. It was an empty warehouse, and we started buying equipment to go into that warehouse. We worked very closely with Ball Aerospace, and that's something that we built on in the years following. Is do we have anybody from Ball here? That's great. We have a very close relationship with Ball. We use very similar software, and we operate 2 of their spacecraft now. It used to be 3, but being that close to them, it was a real benefit. And if you talk about the history of LASP, there were LASP professionals that actually started Ball Aerospace. And there was a talk last year or 2 years ago, talking about the history of LASP and how it's tied to Ball Aerospace. So we used their simulator, and then we went to the Goddard Space Flight Center, and we used their ground network system. So the little red dots on the map are places where they have antennas. These are the antennas that we used to communicate with the satellite. And it flew over. That's how we would get commands up to it and science data back down. And we also used Goddard's Flight Dynamics facility, which is we still use that today for some missions, to give us the orbit data, exactly where that spacecraft is located. This is kind of cool because if you're, let's see, older than 30, you're maybe familiar with this, maybe 40. Tape drives. Who remembers tape drives? Yes. So we actually had tape drives. And I think a lot of these tape drives you could now put on a thumb drive, probably more than that. But this is the kind of equipment that was considered state-of-the-art. This is something too. We bought a PDP 1134 built by Digital Equipment Corporation, DEC. And that's the beautiful thing over here, even with the modern chair. And so then you look at it compared to your little iPad. Processing capability, 1,000 times what, the iPad's 1,000 times more than what we had in there. 1,000 times more memory, 100 times more storage. But again, this was state of the art, and we were thrilled to be using it. If we couldn't get our hands on equipment, we had some really smart people that could build their own. So we actually built a block error detector, and I believe that was built in somebody's garage and then brought in. One of the cool things we did was we went state of the art and spent big bucks back in late 1970s on color monitors, because nobody had color monitors back then. And for a mere $1,400, you could get a really nice color monitor. Unbelievable back then. Unbelievable. So it was interesting, I guess, when NASA came and they saw, wow, you guys have color monitors. We don't have color monitors. So yeah, they were pretty thrilled with that. The software, we actually went around, again, looking for what's available. We didn't have the time at the moment to do the software, so we went to Johnson, we went to JPL, we went to Goddard, and actually found software at Goddard that we could use for the command and telemetry part of it. And as a lot of you guys know that do software, taking somebody else's software and putting it on your own system hardly ever works right the way you're supposed to. So we had a lot of nice features, but at the same time, a lot of people have put a lot of work into making that software do what we want it to do. We built software of our own for handling the data, for handling all the scientific data. The software we used mainly was IDL, and IDL is software that many scientists are very comfortable with, and it actually started by somebody here at LASP, who developed IDL and went off to form his business and did very well. But we also used IDL with Mariner 9 and Possel. But we did develop a lot of our own software, planning and scheduling, attitude determination, and then the satellite engineering analysis was developed here. Again, with some really fancy equipment. The mission was very successful, and I hope you had a chance to hear Gary Rotman's talk in October. But a lot of science was, really cool science was done back then. We did have issues. The recorder failed on us. It was supposed to be a 1-year mission, and it lasted 7.5 years. So it was a well-built spacecraft, well-built instrument, and but a lot of times when these satellites get old, it's the older the satellite, it's kind of like it takes more care and feeding. And so the operations team at that point had a lot of different issues. We had a lot of good scientific campaigns, but we didn't have quite the tools that we have today. A lot of our stuff today is automated. So when the satellite flies over a ground station, if we're not sending a command, we've got software that monitors for us that satellite. Back then, they didn't have it. So we had people here, professionals and students, every time the satellite flew over one of those ground stations to make sure it was a healthy satellite and nothing was going wrong with it, and that we were getting our science data back. 1989, I guess it is, we lost contact with it. So at the end of that time, it was still collecting science, and it was still doing well. There was no fuel on board, so it was a natural decay coming in. The list of students. So everyone in this list went through our training program. They supported the satellite. They learned hands-on what it was like to operate operate a satellite. Many of them went on to bigger and better things. Several of them we were able to keep at LASP, and they're now senior engineers at LASP. One person, I mentioned the Mars program that we have, manoeuvrin. Guy Beetlejuice is the program manager for manoeuvrin. So he's the program manager at Lockheed building the satellite, and he got his start here at LASP on the Solar Mesosphere Explorer. So there's probably several others that are doing wonderful things out in industry because of that start they got here at LASP. So after SME, we didn't have another spacecraft for 15 years. So we did a lot of the software development of the tools that we currently use on our spacecraft. The command and control system that we used, we developed a system called Oasis CC. That's a system that today Ball Aerospace uses quite a bit. Our friends at Digital Globe, if you're familiar with them in Longmont, that they operate imaging satellites. They originally used Oasis CC, and they've since moved on to something else. But it's the same software that's been used on lots of different satellites. We also built an interesting and very powerful planning and scheduling, and the software we used here is something that we use again on all our missions. We started back with SME, we refined it, and now it's a mainstay for scheduling our instruments and spacecraft commands. Modern tire for 1970s. Anybody have slacks on like that? Yeah. So after that, lots of different spacecraft, and I'll talk more about each of these. Well, I'll talk more about the ones we're operating today. STRVs were done in the 90s. Snowy was done in the 90s. And we've got other spacecraft that we're doing now. We're currently operating 4 spacecraft. Source is looking at the solar radiance. Tom Woods, you probably have seen talks by Tom about what they're doing with the sun measurements. He's the principal investigator, the lead scientist for that. QuickScat is a mission that Ball Aerospace built the spacecraft. JPL is managing it, and it's studying the ocean surface winds. And that's been the mission that's been going on since 1998. So again, it's a spacecraft that's old and, yes?
Didn't QuickCat just fail recently?
So it has a microwave scatterometer that is spinning, and the spinning part stopped. And so it's now fixed. But it's still collecting science, and NASA keeps paying us to keep operating it, so I assume it's doing cool science. So I think we're funded through next July, and I think the year after that too. So everything works. A lot of these spacecraft, though, there's issues with all of them, and we're trying to keep them alive with Band-Aids and baling wire. ISAT is a mission that we had for several years. It was studying the ice sheets over the northern hemisphere and Antarctica, and it used a laser altimeter, a series of laser altimeters. The lasers failed, and so we had to deorbit that one. So LASP has experience of bringing a spacecraft and re-entering it, using a ball as fuel and re-entering it. And I have a funny story after that, after this chart to talk about that. AIM is running a device in the mesosphere. I mentioned that one. We launched that in 2007. Kepler is the one that's out in front looking for planets, and we launched that in 2009. And as I said too, if you go down the hallway here, the center hallway, we operate lots of different instruments on different spacecraft. And these are just a few of them. Cassini, Messenger looking at Mercury, and then New Horizons on the way to see Pluto. So ISAT was really interesting because we it had fuel on board, and there's good stewardship of space is if you have fuel on board, you should try to deorbit your satellite so you don't have space junk up there. So we were directed by NASA, let's use up all the fuel and bring it down as fast as you can. And so we did all the planning, maneuvering, working with Ball again. That was Ball Spacecraft, and we brought that in. It was quite an event. Again, we've never deorbited a satellite before, so that was a first for us. And so it got a lot of publicity. If you followed the last few months, there have been other satellites that have come down, and a lot of times you can't predict where they're going to land. You can just know they're going to come down. And ISAT was one of those. It's not as large as some of the other satellites coming down, but it was a good-sized satellite. So when it finally re-entered, we did a press release, and NASA did a press release that it came back. So one of the British newspapers came in and did a little tongue-in-cheek article here. U.S. undergrads crash NASA satellite into Arctic. Undergrad students in America managed to get control of the maneuvering thrusters of an orbiting 2,000-pound satellite at the weekend, sending it plummeting into the Earth's atmosphere to rain burning fragments across the chilly seas north of Norway and Russia. Part of that's true. We think it landed somewhere in the North Sea, in the seas north of Norway, out in the ocean where nobody got hurt, but nobody saw it actually land out there, so it might have all burned up in the atmosphere. And they had another line in here, something about, where were the professionals? They were out in the back having a cigarette. So we didn't put that press release out. So not quite true. It was later in the article that said this is not true, that we really, NASA did, students did bring it down, but it was under the stewardship, under the direction of professionals. But I did get calls from NASA saying, why did I release this press article? I didn't. I don't get any press. So mission operations, what we do here with all our satellites is we support launch and spacecraft testing. In the Air Force, we used to call it on-orbit testing. Here we call it commissioning. That takes a lot of planning. We do a lot of rehearsals before it's done, testing software, testing procedures, making sure everything is ready to go. You throw in anomalies in practice to give crews a little stress. What happens if the solar array doesn't deploy all the way? What do you do? What if your lead ops director comes down with the flu and is out for the day? We do stuff like that. So once we do get the spacecraft up in orbit, it comes to the mainstay of the program: orbit determination, planning and scheduling, spacecraft events, instrument events, command and control of the satellite. And then a big one, and this is where we have student involvement, is monitoring the health of the spacecraft. And I'll talk more about that later. Anomaly resolution. This is key to keeping these satellites alive as long as they are. When there's an anomaly, most of the time you pull in the engineers and you pull in the people that built the spacecraft along with the operators along with NASA, and you try to get that spacecraft back working. And if you can't get it back the same way, you try to figure out what else you can do with it to make it functional. We have some spacecraft that we have anomalies that were never planned, and we're still collecting science with it. We're still getting a lot of bang for the buck for your tax dollar. We maintain our software. We have a very strong software team, again, involving students, and then we archive the data. For each of our missions, we have a full-time professional that is the flight director, and that person's in charge of the mission. Our ops people, as I said, our staff is about 50-50 professional and students. Everybody goes through a screening process, and that's required by NASA. Basically, an agency check. You know, are you a drug dealer? You know, are you a murderer? If you're not, you're okay. So we'll bring you in. A little more strict than that, but one of the nice things too about the way we do spacecraft development is we're involved very early in building the spacecraft, and we're involved in the testing of it, the integration and test of it. So the same people that operate this have seen it on the ground, have sent commands testing the software to make sure it works on orbit. And then we have these procedures that we continue to improve with every mission, and both on our software development, on our ops, and well-established procedures. Not everybody can get on the web to send commands to the satellites, so just be sure, just make sure you don't get that impression. You know, we are a university, so we're open, we're here, but it's a locked room to get in there. You have to have passwords to get into the system to send commands. So that's all secure. The data dissemination, we try to get the data out to scientists, but one thing nice about this is we've got software set up that, you know, when I talked about the SME students, they had to be here every single pass to look at the data. The professionals and students here, we have our iPhones, and I can look at telemetry from the spacecraft on my iPhone with the right passwords. So it's not staffed 24 hours a day. And we use a lot of our existing software. So when it comes to the training, we have at least for the mission operations, well, as I mentioned, we employ students, both undergrad and grad, in everything that we do here at LASP. The idea of this hands-on experience is so valuable when you go back and you talk to the students that graduated and they go into their jobs. It's like they've got 2 to 3 years head start on the people that graduated with them, because they've got this hands-on experience. They've gone through a satellite battery anomaly. They've gone through a wideband antenna failure. They know what it's like to work as a team with professionals, with engineers, trying to resolve problems. They understand the space business. There's pressure, especially when you're dealing with spacecraft anomalies, and they have to follow procedures and standards. This is not something we take very lightly, and we have very strict procedures that when you do command a spacecraft, you follow these procedures. If you screw up, we have boards that meet, and you're in the board, students with the professionals, going through what went wrong, why it went wrong, and how to make sure it doesn't happen the same way next time. Our students are, as I mentioned, they're paid positions. We make them work about 20 hours a week during school year, 40 hours a week in the summer, and that's a heavy load. One of the things that the students realize once they finish the training in the summer that we provide is they get to load with school, and then they still have to come in for their 20 hours. It's not easy. We do go through all aspects of our of the operations. We train them. We usually look at them at the end of their sophomore year, and that's mainly to give the students an opportunity to experience college life, where as a freshman, get a little bit better established as a sophomore, and then jump into it, be able to take on this extra workload once they're juniors. And on the ops side, we'll take any major that's out there. Most of ours are aerospace engineering, but you don't have to be. We've had theater majors, we have music majors. If you're interested in space and willing to do the work, we'll train you. But again, you have to be willing to do the work. And then our students are assigned to subsystems. I mentioned that monitoring the spacecraft. One of the jobs they have is every day, as the spacecraft sends telemetry down and understand what's on the spacecraft, how the systems are doing, the student's job is to look at that telemetry every day, make sure there's nothing going wrong with instruments or with the spacecraft. We do classroom training, we do hands-on. This is all done in the summer. That's about a 10-week program. Again, we cover all aspects of operations. At the end, they go through a series of written exams and then practical exams. The written exams, you've got to pass with a certain score. The practical ones, you're sitting down with a professional next, and watching the professional do the commanding, and then the student is responsible for the commanding with the professional sitting next to them. And then there's a session where the professionals basically grill the students. Do you know this? What would you do in this case? Just to make sure they're really understand what they've been taught. When we had the ISAT deorbit, New York Times heard about us also, and so we did a telephone interview. We had a professional, obviously, that was sitting with the student, but the students are the ones. The student terminal is the one that actually sends commands to the spacecraft. The student that was on for ISAT, the New York Times wanted to interview the students. So we did this by phone, and this is what he wrote. It's got to be the coolest student job on the planet, or for that matter, in the solar system. So that's actually out of the New York Times. I use this chart to recruit students. I go to some of the classes, and we have other professionals that go and talk to the classes. But we kind of talk to them about what it's like to be a student command controller, the classroom work, talk about the spacecraft. Spacecraft are loaded. We send commands to the spacecraft, and the students are in charge of the telemetry and monitoring spacecraft. But it's a real job, and I think one thing I forgot to mention is, so students are assigned these 20 hours. We have coverage, somebody on call right now through the night, both professional and student. If one of our spacecraft has a problem, that student has to come in. We'll call that student in. I know they've got finals next week, so we're slacking off a little bit. We give them finals week off. We did when we launched Kepler, I believe. Kepler, we made them work through finals. But normally, professional will take over. But on a routine basis, we bring in students, no matter what the shift, no matter weekend, holidays, we bring the students in to support the anomalies. It makes it a real job. If you're on call, you're not going to go out Friday night and have a beer with your friends because you're on call. You might not be called in, but there's potential, and I'll fire you if you come in smelling a beer. So we take this, again, very seriously. So again, for the students, I could say, you got to work hard. We'll take any degree as long as you work hard. It helps if you got some sort of math, physics, engineering background, because you understand some of the basics of spacecraft and orbits. But again, if you're willing to learn it, you can do it. And it's a hands-on experience, helps you thinking 3D, thinking critical, thinking as a project, helps a lot too. So with that, we have one more mission that is coming up, and That's what we're working on next, but don't tell anybody, okay? Anyways, that's the end of my talk. If you have any questions? Yes?
I'm just wondering where Kepler was pointed at, like what area of the skies, what star system?
It's looking at between Cygnus and Lyra, the constellation Cygnus and Lyra. And it's, if you go in the lobby here, right out here, there's star pictures of all the stars, and it's in the field of view. So it's that area. Yeah.
Bill,
Yeah.
now at Goddard quite regularly nowadays, they have orbit debris or they do inclination adjust maneuvers that do something to avoid space debris. And they're monitoring things down to grapefruit size, basically, by
Yeah.
NORAD or the equivalent.
Yeah.
Have you had to do inclination adjustment? Well, inclination adjuster schedule. Did you do
Yeah.
orbit adjust, orbit avoidance?
Yeah, so the ones, so AIM and SOARS don't have fuel, so we can't really cannot maneuver those. QuickScat has fuel, and ISAT has fuel. ISAT was the only one that they were concerned with debris one time, once or twice. And there's so much uncertainty about where that debris really is and where it's going to go that in the end we started doing analysis. There was such an error margin that we said we don't want to take a chance of moving and perhaps making it worse, moving it into the path of the debris. But it's a problem that, you know, it's going exponential. You know, especially with the Iridium and the Russian rocket that collided, and then the Chinese that had the anti-satellite that blew up their own satellite, but a whole bunch of debris out there. So it's going to be something we've got to worry about more in the future. But only ISAT was the one that we ever considered maneuvering, and then we never did.
If you break the whole industry down into, say, segments like private, governmental, and what we are here,
Yeah.
who are the big employers? Where would you expect to end up if you were in business?
So the ones that do the heaviest recruiting is JPL, Jet Propulsion Lab in Pasadena. Several students go there, but most of it is industry. So it's Lockheed, Raytheon, Northrop Grumman. People that want to stay local tend to go to one of those companies. And we've had NASA Goddard out here recruiting. It's a little bit more difficult because there's civil service positions and you've got to go through a more intense application process. But again, JPL is a big one, and the big aerospace companies are the main recruiters. One of the ones that just locally was recently started coming is EchoStar. EchoStar is in Cheyenne, Wyoming, and they operate 12 geostationary satellites that do dish network. They do dish network, and what's that?
They just launched a new satellite last month. So you're the
Okay.
one that was out of orbit.
Right. And they're so we've had tours up there, and they're very nice people. They've come down here and they recruited. They interviewed 5 of our students last year and offered all 5 jobs, and all 5 students turned them down. And I said, why? Well, it's Cheyenne. Well, you're not going in. Why do you even interview? So if they ever move operations to Boulder, it might be easier for them to recruit LASP students. So
Accidental property there with the bison.
yes, right. Yeah.
When you're talking about discovering Kepler 22b, why did it need to be seen 3 times?
It's a science thing. Scientists like 3 data points to confirm it's real. And a lot of these stars, there's variability in the stars, sunspots that go over these that could make it look like it's a planet. There's noise in the detectors that they're using. And so they want three events at the same time, like the same separation, to confirm that's really a planet and not something else going on. That's why if you look at the Kepler website, they talk about having 2,200 candidates for planets. So they're not confirmed planets yet, but they think they are. But they want to get a few extra data points to confirm that they're planets. Yeah.
What's the relationship with the ground stations for sending the data and receiving it?
Yeah, so we have a relationship with Goddard, the ground network folks. They schedule, they know our satellites, they schedule the ground contacts, they know the orbits, so they schedule the ground contacts, and then we work with them. They send us when those contacts are going to happen, and we schedule what commands we're going to send up to the satellites at that time.
And then for downlinking, is it
And the
almost real time, or?
Yes, it's real time, comes down, and it gets sent to us, and then we make sure it's a complete set of data. And if it's, and 90% of our problems are with ground stations, and that we don't get the data completely. So there's something funky going on at the ground station, and they have to retransmit. So our guys, when you're on call at night, you can still do it from home, but you've got to call the ground station and say, hey, resend the data. But we also, on the AIM spacecraft, or Anomaly here, we use a NASA satellite system called TDRS, and those are relay satellites. And so we collect data from AIM with those satellites. We schedule those from White Sands, New Mexico. That's where their office is, and it's all students that does that do the scheduling for that. So it's a student-led job for them to do that. Yeah.
So do you do your testing and commissioning with Goddard as well?
It depends on the program. So we do it with the spacecraft builder. So if Goddard's building the spacecraft, we'll do it with them. If Possel building the spacecraft, we do it with them. If Orbital Sciences builds it, then we test with them. So it really depends on the spacecraft builder. When we do Maven, we'll do with Lockheed and the instrument teams. Yeah.
Well, has your control center ever been hacked?
Never. No.
With the Goddard, when the controls Terra spacecraft, it got through several firewalls, all within one firewall of getting in. It was detected. It's not public information, but
Okay.
it was very close to the biggest satellite NASA's ever had in our science.
Yeah.
So some.
We take that very seriously too. We have security policies that from Goddard that have been given to us, say you have to have these security procedures in place, and we get tested every 6 months. They test our systems. They run programs that can
Try to penetrate.
penetrate. And once a year, they actually come out and they do scans of our systems. And we've always been top notch. So it's kudos to our IT team that supports us, that they know what they're doing, and they're keeping us safe. Yeah.
Do you have any idea why this program has been so successful?
So there's a couple things. One is I think we have LASP in general has been successful because you've got a very dedicated team of scientists and engineers that just love this work. I mean, they absolutely love it. Give up family life, give up holidays, weekends, because they really love doing the work, and they take great pride in the work. And so the professionals that have been here, I think, show that pride, and that's a strong influence on students. And so when you're working with a team like that, when you're working with people like that, it just leads to success. I think that's the bigger picture of it. There's a financial side of it too. If you're looking at how much it costs LASP to operate a spacecraft, and you look at a company, how much it costs them, LASP is part of a university, so we don't have the profit center, we don't have a profit fee. Our overhead's pretty low, and even though we pay students better than McDonald's, we don't pay them like professionals. So if half their staff is underpaid students, it's a good deal for NASA. So financially, it makes sense for them to come to us also. And especially once you have a track record like we have, it's easier for them to accept the risk of paying their students operating on their spacecraft. I think that adds to success too. Yeah.
What's the success rate of students who apply for the job and actually go through the training and get the job as a result?
So it's about and it varies depending on our budgets and how many spacecraft. When we lost ISAT, we couldn't hire as many students because we didn't need them. So it depends on how many spacecraft we have. We try to hire about 10 students a year. We probably get 50 applications, and out of the 10, it's usually about 80% that make it through the summer training, and then over the next several years, usually the first semester, they realize, like I said, it's a job, and I have to do this job along with schoolwork, and I'm seeing my grades go down, and I can't do 20 hours a week anymore. So that, one or two will drop out, and then during the process, things happen in somebody's life, things change, and people will drop out. So I'd say 60–70% make it all the way through. It's a tough program, but again, extremely rewarding when it's so easy for me to help students get a job, because you put on that resume, I've got my degree from CU, and oh, by the way, I flew spacecraft in college. How many people can say that? And so I think companies that are looking, I think they appreciate that kind of experience. So they seem to do pretty well. Yeah?
I understand you're from the Air Force. Would you care perhaps to speak about the drone that crashed in Iran?
No. Nothing. Absolutely nothing. I don't. I don't. Yeah.
How many students stay on the LASP?
It does vary. If we have an opening for a professional, it's so easy to say to a student, I'll take you. But then I don't feel that's really our job either. I think my job is to get students to go out in the big world and experience something beyond university life. And so I'm very reluctant to do that. But we have taken a few of them, and they do really well.
And how many come back from industry then?
We've had a few come back from industry, yeah, which adds a lot too. Or they've worked at another university and they come here. So it's great to bring somebody that has an experience from somewhere else and bring that experience into LASP. So it's not just LASP your whole career. It's kind of like grad school, right? You don't want to keep going to the same school all the time. Any other questions? Well, thanks a lot. Hope you appreciate it.